So we've talked about approximation algorithms. Right, here we are. And we've designed and analyzed an approximation algorithm for the metric traveling salesperson problem. That is the traveling salesperson problem with the additional hypothesis that the edge weights satisfy the triangle inequality, which seems like a natural hypothesis for practical applications, but from a purely mathematical perspective, it is conceivable that there are graphs with edge weights which do not satisfy the triangle inequality. And actually, at the very last slide of today's lecture, we're going to encounter to construct exactly such an instance and then prove that in this case, the traveling salesperson problem cannot be approximated. So here, approximation is really a crucial part in order to make to enable such a polynomial time algorithm. That's the point, right? Traveling salesperson problem in general is an NP hard problem, so we cannot hope, we cannot expect that to admit a polynomial time solution, at least in the exact case, but approximately this is possible. And here approximation algorithm is with emphasis on algorithm as opposed to heuristic. As you know, the difference between an algorithm and a heuristic is that an algorithm comes with a rigorous analysis, and this is exactly what we did. So the algorithm we have discussed is called Christofides algorithm after the name of the author, and it's actually on a high level, it's a simple algorithm. First step is first compute a minimum spanning tree. Well, this is only a simple step because we have previously discussed many ways of computing minimum spanning tree, Kruskal's algorithm, Prim's algorithm. We've discussed underlying data structures for getting this performance of this algorithm down to m log n essentially. But all of this for here it suffices that this is a polynomial time algorithm. And then the second step, or rather second phase, is traverse the tree just computed, traverse it in depth first, pre-order. Again, this is not a simple instruction, but this is another meta algorithm traversal, entire sequence of instructions, but you know what is meant with that instruction. So let's discuss some examples of this algorithm. Suppose we have this configuration of nodes, and this is the minimum spanning tree produced by one of the algorithms. Then the Christofides algorithm in the second phase will traverse this minimum spanning tree in depth first pre-order, right? So we can start with any vertex, right? Any vertex can serve as root to a tree, but in this example for the slides, we've started with the vertex A, then traverse depth first, pre-order. So first visit A, then visit its left subtree, then visit its right subtree. When recursively visiting its left subtree, first visit the root B, it's in order, it's pre-order, then its left subtree, then its right subtree, and so on. So that means the traversal proceeds the edges here down here, then up again, then here, then up again, then up, and then the same here, left, up, right, up, 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 and back. So that's the pre-order depth first traversal of a tree. in this example. And as you have seen, this traversal is not a tour, right? So we visited A, B, C, B again, H, B again, A again, and so on. So this is not a Hamiltonian, this is not a tour, right? So we visited many vertices several times. And therefore, in order to make this really a cycle, we're going to make shortcuts. So instead of going from A to B to C, and then B and H, we're going directly from C to H. And thus avoid visiting B again. And only this makes our algorithm produce a tour, a cycle of the graph, right? So after H, we take a shortcut. We don't return to B and to A before proceeding to D, but we jump directly from H to D, then visit E, then F. So now the backtracking is again replaced by a shortcut, E. Instead, we go directly from F to H. And then again, the backtracking H, G, E, D is skipped. And from G, we go directly back to A. So that the resulting tour in this example is A, B, C, H, D, E, F, G, and back to A. Okay, so this is a pre-order depth first traversal, and that's a resulting tour that I just mentioned, and that's a sequence of edges traversed. Now, as you see, not all edges were present here, but we suppose, without loss of generality, that we have a complete graph, and only that some edges are more expensive than others to model. When edges are absent, we replace them with edges that are present, but just very expensive. But all of this, underlying all of this, is the hypothesis that the edge weights satisfy the triangle inequality. And now if you look closely, indeed, that's we've used that already in the design of the algorithm. Namely, when we go from B, instead of going from C to B and then to H, instead we jump directly from C to H. And intuitively, that should be no more expensive, right, than the original detour followed by the traversal. Going from C to H directly should be no more expensive than going from C to B and then from B to H. And rigorously, this is exactly what the triangle inequality asserts, that taking a detour is no shorter, could be equal, but it's no shorter than jumping directly from C to H. So taking these shortcuts only makes sense because we have the triangle inequality. And it was reflected in our formal analysis of the algorithm of its approximation ratio. Approximation ratio is the method to analyze approximation algorithms. That's our measure of performance. Recall that in this lecture we've had many different measures of performance. For instance, competitive ratio was the way of measuring performance for online algorithms. Expected running time was a measure of performance for randomized algorithms. And for approximation algorithms, our measure of performance is, well, actually twofold. The first is polynomial time, but we don't really care so much about which polynomial time here. Instead, the main measure of performance is the approximation ratio. An approximation ratio is the ratio between the approximations achieved by the algorithm we have designed in comparison to the optimal solution, which we or which one cannot in general compute in polynomial time, since we're talking about NP-hard optimization problems here. And this is kind of the challenge of approximation algorithm analysis. How can we compare the quality of the solutions they produce to the quality of an optimal solution, which we don't know? And in this example, with a metric traveling salesperson problem, this is how we solve that kind of conundrum. So we consider some intermediate quantity. So C denotes the tour, the cycle produced by Christofides algorithm. So in this example, it's the cycle A, B, C, H, D, E, F, G, A. And C prime usually denotes the unknown optimal tour. Prime is a symbol for optimal. Let's say in this example, this is the optimal tour, but only we know that in a sense in our analysis. And the intermediate quantity which we use to compare both is the set F. That's a set of edges traversed by the, or the set of edges, the sequence of edges visited by the traversal. So T is the minimum spanning tree with these edges A, B, C, B, C, B, H, A, B, and so on. And F is the set of edges as they are traversed, the sequence of edges as they are traversed by the tree traversal. So F in this example is the sequence, this edge from A to B, this edge from B to C, then again the edge from C to B back, then the edge from B to H, and the edge from H to B back, the edge from B to A back, and the edge from A to B, and so on. And an important observation is that one relation between the edges in the minimum spanning tree and the intermediate sequence F of intermediate edges is that every edge in F is exactly double occurrence of the edges in T. So let me make that formal by reminding you of the notation that we used. So when we have a sequence of edges, then we would abbreviate the length of the sequence as the sum of the weights of the edges. We call that we have edge weights, and we're carefully distinguishing here between sequences of edges and sets of edges, because as we just saw in the example of the set F, the set of edges traversed during the traversal, some edges occur twice, and in a set, of course, every edge can occur only once. So that's an important difference between a set and a sequence of edges. In a sequence of edges, edges can occur twice, and we need to use that here in our analysis. So, and so what we want to prove is that the solution produced by Christofides algorithm is never worse than twice the cost of an optimal solution. So as with competitive analysis, this is a relative measure of performance. So we take any input and kind of hypothetically perform our algorithm, hypothetically perform an optimal algorithm, and then compare the two solutions, the cost of the two solutions, and then take the quotient of the two costs. And here we're going to show that this quotient is always less or equal to 2. So that Christofides algorithm is never worse than an optimal solution. And this is good enough, right? So many applications, boiling down the running time from exponential for an NP hard problem, optimization problem, the best we can hope for is exponential time solution. But here we can boil down, in approximation, we boil down the running time from exponential to polynomial, and we only have to suffer a factor of 2 loss in quality of the solution. So that seems like a reasonable way of dealing with NP-complete problems, which most likely don't admit a polynomial time solution. So in order to prove that this factor 2 of the bound on the ratio to prove that Christofides algorithm returns a tour of cost at most twice the cost of the optimal tour C prime. We're going to establish 3 inequalities between various quantities that occur only in our analysis. And when putting together these 3 inequalities, they yield this factor of 2. So the first inequality is that the length, the sum of the weights in this terminology of the edges constituting the minimum spanning tree is less or equal to the cost, the sum of the weights of the edges produced by an optimal tour. Okay, let me say it again. So as part of our algorithm and therefore also as part of our analysis, there's this minimum spanning tree produced along the way by one of the algorithms, Green's algorithm or Grosskal's algorithm. And the claim is that the total weight of this minimum spanning tree, the sum of the edge weights, is no larger than the cost of the optimal tour, the sum of the edges constituting the optimal tour. That's our first inequality, and it is true because remember, minimum spanning tree by its very definition is a spanning tree, so it's a tree and it connects all vertices, and it's minimal, meaning that among all possible trees that connect all vertices, this is one of minimal cost. Now let's compare this to the tour, to the cycle, to an optimal cycle, which we don't know, but one thing for sure we know is that it's not a tree, right? Because, well, it contains a cycle. But on the other hand, if from this cycle we remove any edge, then the result is a tree, right? It's connected and it contains no cycles. That's the definition, one of the definitions of a tree. So when we do that, we take the optimal, unknown but optimal cycle and remove any edge, then there's going to be a spanning tree, and therefore its cost must be at least as large as the cost of a minimum spanning tree, right? Minimum spanning trees has by its very definition cost less or equal the cost of any other spanning tree. On the other hand, if we remove an edge from the optimal cycle, then the cost of that cycle, or the resulting cost of the resulting set of edges, the cost of the resulting spanning tree will only decrease. So therefore, the cost of the minimum spanning tree will be still less or equal to the cost of the original cycle, which optimal cycle, because that includes the edges we have just removed for temporarily for purposes of analysis. So this establishes our first inequality relation between the cost total weight of the tree, edges in the minimum spanning tree, and the total weight, the cost of an unknown optimal tour. Now, for the second inequality that involves this intermediate quantity f, the sequence of edges as they are pursued, traversed during the graph traversal, not the way the sequence of edges that Christofides algorithm finally outputs, but in this graph traversal, every edge is actually pursued twice, once going forth and once going back. It's just because we're talking about undirected graph, this is always possible, right? So that's basically kind of the backtracking or recursive traversal algorithm for such a tree. And since every edge is pursued precisely twice, the total weight of the edges in this sequence f is precisely twice the total weight of the edges in the minimum spanning tree. And that's exactly what our second inequality, which happens to be an equality, what this equality says. And the third inequality and final inequality says that the cost of the tour produced output by Christofides algorithm is less or equal to the cost, the total weight of the edges as pursued in the way they are pursued by the graph traversal. And this is really where the triangle inequality comes in, as we've already mentioned, namely, so for instance, the difference between this f and c here is that f one would go from A to B, and that's also how one would the algorithm would output in the tour C. Then from B to C, that's again the same for both, for F, capital F and capital C. But now comes a difference. In capital F, one would go back, traverse this edge a second time, and then go here, traverse this edge a first time. Whereas in the output of Christofides algorithm would take this shortcut, avoid visiting B a second time. That would not be a cycle, instead going directly from C to H. And going directly from C to H has costs less or equal to going from C to B and from B to H. And that's exactly because of the triangle inequality. In general, this is not true. In general, one could happen that going from C to B and from B to H is actually cheaper than going from directly from C to H. And we're going to encounter such an instance at the end of today's lecture. So to summarize, now we have established these three inequalities between various quantities that we have introduced for the purposes of our analysis. What we're actually interested in is a relation between the cost of C, that's the cost of the cycle produced, eventually output by Christofides algorithm, and the cost C prime of the unknown optimal tour. And this is really, I mean, now we have a handle on the cost of this optimal tour, which is the key, right? We don't know really much about the optimal tour, but still we have to compare that in our analysis, and that's what the purpose of inequality 1, to get a handle, to get a lower bound on the cost of this unknown optimal tour. And if we now plug all the inequalities together by transitivity, that means the cost of the cycle output by Christofides is less or equal to the total weight of the edges as they are pursued by the graph traversal, that's capital F, right? That's inequality number 3. Then comes equality number 2, the total weight of these edges as they are pursued in the graph traversal is precisely twice the total weight of the edges in the minimum spanning tree, because every edge in this tree is pursued precisely twice. That's equality 2. And finally, inequality 1 says that the cost of this minimum spanning tree is at most the cost of an unknown optimal tour, and therefore also twice the cost of this is at most twice the cost of that. And so putting all these things together, now we're really in business, right? Now we see that the cost of the cycle output by Christofides algorithm is at most twice the cost of the unknown optimal tour. And this is what we wanted to prove. This is the approximation ratio of Christofides algorithm is at most 2. So this concludes a recap of last lecture. This the proof of the approximation ratio of Christofides algorithm. And maybe we'll make a homework where you're asked to produce an example graph where actually a factor of 2 ratio is attained, which means that we cannot improve our analysis. Our analysis of Christofides algorithm is tight. One can imagine maybe better approximation algorithm yet yield better approximation ratios, maybe 1.5 or whatever. But at least Christofides algorithm cannot guarantee a better approximation ratio than 2 that may or may not become a homework problem. Okay, so so much about Christofides and approximating the minimum metric minimum traveling salesperson problem. And let's now take a very brief break, just a minute. And we're back. So if you have questions, now is the perfect time to ask. No questions? Okay, right. So after this this recap, we now move on to another approximation algorithm. Namely, we're going to approximate the knapsack problem. And one important difference between Christofides algorithm and the approximation algorithm for the knapsack problem we're going to discuss now is that Christofides algorithm attains one approximation ratio, factor of 2. If we want a better approximation ratio, then we may need a different algorithm, and actually such algorithms exist. But their different approximation ratio means a different algorithm. What we want to discuss here is approximation schemes, where one algorithm can attain many arbitrary good approximation ratios. Namely, one can approximate the problem, optimal NP-hard approximation problem, better and better with arbitrary desirable approximation ratio. But of course, one expects the running time must also blow up as the approximation ratio blows up. This is called approximation scheme. It's kind of like a family of approximation algorithms, all with different, better and better approximation ratio. So that's an approximation scheme. But before introducing that, let's recall what is the knapsack problem. And there are several versions of looking at the knapsack problem. So one version is, right, so basically the underlying ideas, there are packets and there's a knapsack. And the packets have weights and they have values. And the knapsack can hold only so much weight before it breaks. And the goal is to put as much value as possible into the knapsack without breaking by appropriately selecting packets. So kind of preference for the most expensive packets and also preference for the light packets. And on this Pareto optimization problem, this is basically what constitutes knapsack. Pareto meaning expensive packets are preferable, but also light packets are preferable. And which packet do you choose if you have an expensive but heavy package, or if you have several cheap but light packets? This is the dilemma basically that is captured by the definition of the knapsack problem, not its solution, of course. Okay, so input formally, right, specification is one of the virtues of computer science. Inputs is a number of packets, n, the number of packets, and they have values, which in our setting is supposed to be natural numbers. So let's say multiples of dollars, and they have weights, which are also supposed to be natural numbers. And there's a weight value bound. That's one way of looking at the knapsack problem when it comes to a decision problem, right? Remember, we have these two ways of looking at problems. One is optimization problem, where the output is supposed to be uh, maybe a subset of the packets, indication which packets to include in order to attain maximum value while minimum weight. And the decision version of that problem says, given that the knapsack can hold weight at most W for weight, and suppose that your kids, your family expects you to deliver gifts of a value, total value at least capital V for value. Is that feasible, right? So maybe instead of the knapsack problem, that's the returning travelers problem, where you can put only so much weight into your luggage for the airline company to allow you to check in, whereas your family who stayed at home expects uh, gifts of a certain value. Well, that was a joke. Okay, so right, this is a decision version of the optimization problem. Is it possible to select among the n packets a subset of the indices of the packets? So S is the subset of packets, such that their total weight, the sum over all the total value, the sum over all the values of the packets that we have selected, exceeds the expectation of your family, while simultaneously the total weight of the packets you have selected, right, the sum of all packets you have selected, the weight does not exceed the admitted weight of during check-in. That's decision problem, because the answer to this question is either yes or no. That's one way of looking at knapsack. The other way is looking at it as a optimization problem, actually at two optimization problem. The first perspective is, suppose we only have a weight bound, so you only have the constraints imposed by the airline. Your total weight of the packets must not exceed capital W, and your goal is to maximize the values. So in this case, the answer to the problem is not yes, no, but the answer is pick the following packets in order to maximize the values under this constraint. And the other way of looking at the knapsack problem as an optimization problem. So here it's a maximization problem. You want to maximize the value subject and while satisfying the weight constraint. And the other is the minimization problem. This is a minimization problem. Here we're given a value bound. Okay, so this is the expectations of your families captured mathematically. The total value should be at least that, and your goal is to pack a knapsack, suitcase as light as possible. So here it's a minimization problem, and that's the third perspective of the knapsack. Right, one is a maximization problem subject to the weight constraints, maximize the value, and the other current is a minimization problem, minimize the weight of your luggage, make it as light as possible, subject to the value constraint. The total value should be at least capital V. Okay, so, and we're going to look, take both perspectives during our algorithm design. So for the purpose here, right, for the purpose of optimization approximation problem, we cannot approximate decision problems. That doesn't make sense, right? There's no such thing as an approximate yes or an approximate no. But for optimization problems, we can approximate, and depending on whether it's a minimization problem or maximization problem, our goal is slightly different, right? So for minimization problem, we cannot beat the optimal minimum. So we cannot find lighter, less heavy choice of the packets that satisfy the value constraint, but being less heavy than the optimal solution. So instead, what we aim for is a solution that is only a little bit heavier than the optimal solution, and a little bit means by a factor 1 plus epsilon, where epsilon is hopefully small. So this is exactly what is written here. So one perspective is we have a hard constraint on the total weight. The airline company is serious. They won't let you board if the weight of your luggage is too heavy, but your family may be a little bit lenient. So if the total value of your presence is a little bit less, a little bit meaning by a factor of 1 minus epsilon less, right? So that's less than 1, then they are still happy. So this is for maximization problems. So here we want to maximize the value, and approximating the maximum means to be satisfied with a little bit less than the maximum, and a little bit less here means by a factor a little bit smaller than 1. A little bit smaller than 1 means 1 minus epsilon for some appropriate constant epsilon that we will talk about later. So for maximization problem, the quality is measured by this factor, a factor which is slightly less than 1, okay? Less than 1 approximation factor for maximization problem. For minimization problem, it's the other way around. For minimization problems, this is the hard constraint. Your family expects to have this value capital V, but maybe the airline is a little bit flexible, and they will let you board if your luggage is only a little bit more heavy than the official constraint. And a little bit more means here a factor slightly larger than 1, namely a factor 1 plus epsilon for a small constant epsilon. So this is our conception of approximation quality for minimization problems, right? So we want to minimize the weight, and we're still happy if we're only a little bit, if we're only a factor of 1 plus epsilon larger than this minimum. Okay, so to summarize, when we talk about approximating problems, then we never approximate decision problems. We do approximate optimization problems. We approximate maximization problems by a factor slightly less than 1, or we approximate did I get that right? Yes, or we approximate minimization problems by a factor slightly larger than 1. Okay, and both apply here to the knapsack. And an algorithm is different from a heuristic in that it comes with a guaranteed approximation ratio, either 1 minus epsilon for maximization problems, or 1 plus epsilon for minimization problems. Good. And in this lecture, we're going to consider the knapsack problem as such a maximization problem. But during the algorithm design and analysis, interestingly, also the other perspective will arise. And this is a reflection of what in the theory of optimization is called primal dual perspective. For those of you who are experts or who will maybe later take courses on optimization. But if you don't, no problem. This is a self-contained lecture on approximation algorithms. Okay, so here comes our algorithm. And maybe what we're going to do is we're first going to design an exact algorithm for a knapsack. Now, since knapsack is NP complete, we cannot expect that algorithm to run in exponential time, but still that algorithm will turn out to be a key to the second phase where we're going to modify that into an approximation algorithm. And so this is a very interesting algorithm. For one thing, it's based on dynamic programming, which is a programming paradigm that you may or may not have learned in CS300 already. So dynamic programming to the knapsack problem, that's an algorithm design perspective. But it's also interesting from a complexity perspective, namely it reflects that the knapsack problem admits a strongly polynomial time algorithm. Well, that's a strange terminology, right? Strongly polynomial time algorithm for a problem which probably cannot be solved in polynomial time because it's NP complete, but strongly here means polynomial time in the values of the inputs. Remember that we usually consider and analyze computational cost independence on the binary length of the input, but here we temporarily switch the picture and analyze our algorithm independence on the value. And for many problems, actually hard problems, they can be solved in time polynomial in the value. For instance, the famous factorization problem, integer factorization, that can be solved by the C for Eratosthenes, for instance, by inner time polynomial in the value of the integer which we're trying to factor. But apparently the basis of cryptography says that it cannot be solved in time polynomial in the length of the integer we're considering. So here we're going to take that perspective and design a strongly polynomial time algorithm for the knapsack problem, exact solution algorithm using dynamic programming. So, and as a first step, let us record that this is no loss of generality to suppose that all the packets have weights that are non-negative, strictly positive actually, and that have weights less than the weight bound that we're imposing in our optimization algorithm. Why is that so? Well, if there's a packet that is that has weight 0, then we're going to include that by default, right? There's nothing is lost by including packet with weight 0, right? It doesn't. It can only improve our solution, the total value of the packets. So only packets with positive, strictly positive integer weight, and for the same reason, any packet whose weight is strictly larger than the weight bound won't fit into the knapsack anyway, so we can immediately discard that. So this is really no loss of generality. Now the loss of not loss of generalities associated with the values. Namely, for the same reason, we only suppose that packets have positive value. If a packet has value 0, then we can discard it immediately. We will never even consider that adding packets without value to our knapsack. And recall that we never have negative weights and negative values because they're natural numbers by our hypothesis. Okay, so this will simplify our analysis a little bit, and algorithmically this amounts to a pre-processing phase. Okay, now we're going to introduce two notations, namely when we fix a subset of the packets, subset S, then we'll denote by small w the total weight of these packets, that's here, and by small v the total value of these packets, that's here. That is convenient notation for the SQL. And our goal, remember, we want to solve the maximization problem. That means we're having a weight constraint imposed by the airline, and we want to determine the maximum value that can be achieved by a suitable subset S of the packets that respect this weight bound. Okay. And we're going to design a dynamic programming algorithm that determines that quantity by gradually climbing its way up on a table, and the table will contain the following mathematically designed values, and then we're going to design an algorithm that fills the table with these values. So let's look at the mathematical definition of the table values. So we have this here, this V, that's a value that's going to serve as a value bound. And this is what I said previously. So here we're going to kind of change the picture. We want to have the value, we have the weight as a hard constraint and want to optimize the value. Here instead, we consider the value as a hard constraint from below. And now we want to minimize the weight. Okay, so this is a dual problem kind of. Or what we really want is to solve the maximization problem, but on the way to that, we solve the minimization problem, but actually we solve a sequence, an entire family of minimization problem parameterized by this parameter m. And the parameter m namely says, only consider the first m packets among the total number of n packets. Does that make sense? Let me say it again. So we want to solve the maximization problem among the total n packets. We want to find a subset of this total of n packets. And to this end, we solve several minimization problems, minimize the weight, subject to actually several value constraints. Here observe that V is also a parameter, and only consider the first m of the total number n of packets, where m will also vary. This is going to be a two-dimensional table, one dimension for the possible values, one dimension for the possible range of packets. And in the end, if we have calculated filled the table, then we can just read off the our solution. Namely, if in the end we set m equal to n, that means consider all packets. That's what we really want, right? Want to consider all possible packets. And also then look at all the possible values that are achievable within a certain weight bound. I'm going to explain that once we've seen the table. Okay, but before looking at the table, let's observe some, mathematical properties. Namely, the quantity we're actually looking for is contained in kind of the last column of the table. That's what I just said. So namely, when we fix the last parameter n to be equal to n. That's what we're actually interested in. So here the last parameter is always n. And now we vary the first parameter v, the value constraint. And what happens if we vary the value constraint? The larger v gets, so does the weight, right? So if we require large value, it means we're probably going to have to carry a larger suitcase. So that as the values here increase, the first argument, therefore also the entries in the table T will probably not, at least they will not decrease. In general, they will increase. That's what this sequence of inequalities is about. And the value we're actually looking for, the result, the largest value attainable subject to this weight constraint is exactly that, where the table entries exceed the threshold weight, right? So remember that the entries in the table represent weights, and as the small v increases, eventually this growing sequence will exceed our hard weight constraint, and that's exactly what will be our answer, namely that's exactly the value v that is just attainable, whereas the next value v plus 1 already exceeds, strictly larger than the weight bound. So this is our first observation. That's basically the reason why we're interested in this table, because it includes the answer to our original problem, our original question, our original optimization problem. And once the table has been filled, this is easy to determine just by actually by binary search in this table, right? So this position where the values exceed in this increasing sequence, where the values just barely exceed the weight bound, this can be found very efficiently using binary search. So once we've filled the table, we're basically done. The next thing to observe is that, yes, that's what I just said. The value we're actually interested in, that's the largest value where the table satisfies this weight constraints. Now let's have a look at the leftmost column of the table. No, the top column is that, I think. So the top column, that's where the values are 0. Okay. So how many packets among the first m packets do you need in order to obtain value 0? Well, obviously no packets at all. So that's and no packets have weight 0. That's why this top column, top row of the table will have value 0. So that's easy to fill. That's the message here. We can easily fill the top row. This may be kind of like Pascal's triangle for computing binomial coefficients. Here, the Pascal triangle, it's the left and left row that is easy to compute, and then from there one can proceed to more inner entries of Pascal's triangle. And what else is easy to compute? The leftmost column. So top row and leftmost column are both easy to compute. Namely, the leftmost column is that where we can only consider 0 packets among our total number n of packets. We can only consider the first 0 packets, and of course, when considering only 0 packets, we cannot achieve any positive value. So when the table entry requires a positive value, then there's no solution, and the minimum of the no solution, the minimum of the empty set is by convention is plus infinity. This is a very helpful convention, like the convention to say that the empty sum has value 0, or the empty product has value 1. That's basically a neutral element with respect to the operation we're considering. Similar here, the minimum over the empty set is plus infinity. The maximum of the empty set is minus infinity. Good, and now comes the interesting final part, namely how to fill the inner entries of the table. In Pascal's triangle, this is exactly this sum of two binomial coefficients yield a new binomial coefficient. Here we want to establish the following formula, that a new entry in the table at position V and M is given by the minimum of two other entries. One entry that is one row up, so in row M minus 1 instead of M row M, and one entry that is also one row up and a little bit to the left, namely V replaced by V minus Vm, where Vm is the value, remember, the value of the mth packet, and plus Wm, that's the weight of the mth packet. Okay, so let me draw the slide now, the table now finally. Here you see the table. So the rows are indexed by m, and our goal is to get m to n. That's the case we're interested in. We're interested in the rightmost column. In the rightmost column, according to note number 1, the entries are growing, non-decreasing towards the end. And we're interested, we want to find the threshold, the position where these growing entries just barely exceed our weight bound. The top row is easy to fill according to property number 3, and the left column easy to fill according to property number 4, and property number 5 allows to recursively fill the table by proceeding row by row, right? And that's possible because every entry here is determined depending only on entries in the previous row. So that's what's indicated by these two arrows. The entry in a certain cell is determined by the minimum of the entries in previous, sorry, I was wrong, not row, columns. Fill the table column by column, because the entries in this cell depend on the entries in the column left to it. Okay, so, and how do they depend on it? Well, recall the notion, the definition of our table. The definition of our table says, take the minimum weight, calculate the minimum weight that is required in order to attain this value, to exceed this value among the first m packets. And so this minimum corresponds to a subset of the packets, right? And this subset either contains the mth packet or does not contain the mth packet. And if it contains the mth packet, then that means if we remove that mth packet, then we have reduced the weight by Wm, but we also have reduced the value by Vm, and the result will be again be an optimum. That's the point. So the result will be the least weight required in order to exceed value V minus Vm among the remaining packets 1 up to m minus 1. Okay, so taking the packets up to m minus 1, this optimal solution, and then add the mth packets will increase the weight by Wm and will also increase the value by Vm. That's a first case where the mth packet is part of the optimal solution. The other cases where the mth packet is not part of the optimal solution, then this optimal solution is also the optimal solution among the first m minus 1 packets. Right? So if the mth packet is not part of the optimal solution, then Um, this is also the optimal weight one can get to achieve value v without considering the m's packet. So it doesn't make a difference whether we allow or exclude the m's packet. So that's the explanation for this last equality. Consider the two cases either with or without the m packet and take the minimum, because take the lesser of the two possible weights. Good, so now we have all the ingredients. We have basically already the algorithm for filling that table based on all this consideration. Fill the top row, fill the left column, and then gradually fill the table column by column according to equation number 5, until finally I filled the table and the rightmost column is the one we're interested in, and there you can immediately easily search for the threshold. And this is a correct algorithm, and this produces the exact optimal solution to the knapsack problem. That's important. It's the exact solution to the knapsack problem is exactly where this last column just barely exceeds the weight bound. And there's already a question concerned with the runtime. So let's look at the runtime and then discuss that. So the claim is that the running time is polynomial in n plus capital V, where V denotes the quantity we're supposed to determine. That's kind of strange, right? That's not the way we usually analyze algorithms. Well, not we, but some people do. This is sometimes called output sensitive analysis, where the cost, the runtime of an algorithm is analyzed in dependence on the input, on the length of the input, like n here, but also somehow in dependence on the output. And this is what happens here. It's actually here polynomial in the value of the output. And this is why it's called a strongly polynomial time algorithm. Regular polynomial time algorithm must only depend on the on the binary length of the input, because how large can capital V be in general? Well, since the packets we are talking about have their weights and values represented in binary, that means their values and weights as values will in general be exponential in n, right? So that's a common difference and distinction between binary length and value can be at most, in worst case, can be exponential. And therefore also capital V, the value of the optimal solution will in general be exponential in n, so that this is not a regular polynomial time algorithm. It's an algorithm polynomial in the binary length n of the input, or the number of packets, let's just say, plus the value. Okay, and Robert has asked, why is this a bound on the runtime? That's a good question. So let's consider that. How many steps does the algorithm make? Well, the running time of the algorithm is essentially dominated by the size of the table, right? Calculating a new entry in the table, that's just looking up to the two entries to the left of the current entry in the column to the left, right? Adding something and then taking the minimum of the two numbers. And this is really possible in time polynomial in n, because this is just performing arithmetic and comparisons among integers whose total length is still bounded by n. So in terms of the binary length, adding one entry to the table, that's possible in time polynomial in n. But how large is the table? How many columns does it have? It has n columns. So that's also okay, right? N is still our main complexity parameter. Doing something linear in n or polynomial in n, that's all good. The problem is the number of rows of the table, right? Because the number of rows, how many rows do we need? How far do we fill the table, right? We may not fill it beyond the part that we're actually interested in, but we're interested in what? How many rows? We're looking for the vth row. The vth row, the row with number v, is exactly the row where the last column starts to exceed the weight bound. So in general, we're looking at v rows. And as I just said, the value v is in general exponential in n. So this is a strongly polynomial time algorithm. Its running time depends polynomially on n, the binary length, but also polynomially on v, the value that we're looking for, which is in general exponential in n. So let's recall Robert's question. Robert asked whether the running time is n times v, and I wrote the running time is polynomial in n plus v. So yes, that's a great question. Thank you, Robert. And the answer is essentially yes, both. So the observe if the running time is polynomial in n plus v, then for instance n times v, that's less or equal to the square of n plus v, right? So if you take the square of n plus v, let's see here. So n times v is less or equal to the square, so therefore it's polynomially, so it's less or equal to polynomial in n plus v, and conversely, n plus v is less or equal to n times v. So if you say polynomial in n plus v or polynomial in n times v, that's basically the same thing. Thank you, Robert. Great question. Hopefully I've been able to answer that and clarify that. So since we're looking from the course perspective of polynomial time, that's basically both the same thing. Great. Okay. So now we have our strongly polynomial time algorithm for the knapsack problem, and it's an exact algorithm. So in the next step, we want to turn that into an approximate polynomial time algorithm. To this end, let's look at in which cases is this a real polynomial time algorithm? Well, it's a real polynomial time algorithm whenever capital V is bounded polynomially in n, right? So if capital V is only polynomial in n, then everything is a regular polynomial time algorithm polynomial in n as well, right? So the bad cases are kind of when V is large, and the good cases is when V is small. And now how can we, there are further cases when this algorithm is actually very efficient. Namely, suppose that all packet weights and values are multiples of, let's say, 1000, right? So let me say it again. Let's suppose that the weights are measured in grams and the values are measured in Korean won. And now we make a transition and round everything from grams to integer multiples of kilos. So whenever something weighs 300 grams, we round it down to 0 kilo. When something weighs 800 grams, we round it up to 1 kilo. When something weighs 1,800 grams, we round it up to 2 kilos. And similar, when something costs 801, then we round it up to Chonwon. If something costs Ichon Yukbek won, then we round it up to 3,000 won. So make everything a multiple of kilograms and of 1,000 ones, right? Then actually we don't need to run this algorithm on the original input, which has very large values, right? But we can replace the number 1,000 gram with 1 kilo. And we can replace the large number 1,001 with the number $1, for instance, right? And thus suddenly improve the running time by a factor of 1,000, right? Does it make sense? Now, by just changing the units of values and weights, and we're by rounding the values of the values and weights, we can improve the running time. We can reduce the parametric quantity capital V and obtain a faster algorithm. Of course, this algorithm does not return the optimal exact solution to the knapsack problem then after writing, right? So actually, after all, we have changed the values, we have changed the weights. But if we do that carefully and observe, or precisely if we only round the weights upwards, and if we only round the values downwards, then that will still be at least a feasible solution. At least the airline will let you board, right? So if you've in your estimating the weight of your luggage, and you have rounded up all weights to integer multiples of kilos, then you're overestimating in the worst case the total weight, and therefore the actual weight will still satisfy the airline conditions. And similarly, when you round down the values, and which means you're underestimating the actual value, then your family will be at least as happy as you have expected them. And this is the basis, this is the foundation, this is the idea that we will apply to this dynamic programming strongly polynomial time algorithm for the exact knapsack problem in order to arrive at the polynomial time algorithm for the approximating the knapsack, actually approximation scheme. So that's all for today. Time is up. On Thursday, we will continue here discussing how to turn this dynamic programming algorithm, exact algorithm, into a rigorous polynomial time approximation algorithm. And then we will discuss also the optimality. We'll see that, for instance, the non-metric traveling salesperson problem cannot be approximated in polynomial time up to any constant factor. Okay, that's all for today. Thanks for your attention. Right, and on Thursday, we will disclose all the details about the final exam date and procedure in the area of coronavirus. Thanks and bye.